Um, just to give you a little bit of context, so Grade2XL is a European funded project funded through the Horizon 2020 program. It has a budget of 10 million euros and it gathers 21 partners in 8 different countries. And we are now halfway through the duration of the project. So Grade2XL is a 4 years long project and it will end in February 2024. The objective of this project is to demonstrate the potential of multi-material WAAM technology for large-scale metallic structures. So as part of this project, we regularly organize webinars to disseminate the research outputs of Grade2XL and to explore one of the aspects of Grade2XL. So today we are very happy to welcome 2 experts who will talk about the environmental and economic implications of WAAM from a circular economy point of view. So first we will have Valentina Pusateri, who is currently a PhD candidate at the Department of Environmental and Resource Engineering at DTU in Denmark. Her research focuses on life cycle engineering, material flow analysis, circular economy and metals, with a specific focus on additive manufacturing. After the presentation from Valentina, we will have Professor Ciprian Cimpan from the University of Southern Denmark, with an associate professor of life cycle engineering, who will also talk about his research focusing on circular economy transition within production and consumption systems, using industrial ecology methods, including life cycle assessment, material flow analysis, and economic assessment. So I will now give the floor to Valentina, and we can take questions, of course, in the course of the presentation. You can just write in the chat if you have questions, and we will ask our experts at the end of their presentation to give you answers. So Valentina, I'll just let you share your slides.
Yeah. Thanks a lot, Lucy, for the presentation. Yeah. So now I will share the presentation. I hope you can see it at full screen. Yeah.
Yes.
Okay, so good morning, everyone. So as Lucy mentioned, I'm a PhD student from DTU, and today I'm gonna give a brief introduction on the methodology of life cycle assessment and life cycle costing, with an example from additive manufacturing or 3D printing of metals. But first of all, I would like to introduce you to the metal manufacturing sector. So the current global carbon emission worldwide are about 28 gigatons of CO2. And as you can see in the pie chart here, industry is contributing about 36% to the global carbon emission, followed by the building sector, transportation, and then other sectors. So let's dig into the carbon emission of the industry. These correspond to more or less 10 gigatons of carbon dioxide emission. And one of the most contributing sector is the steel manufacturing sector, that is about 25%. And this carbon emission corresponds to about 4.4 million tons of steel produced per day. So these are very high numbers, and we should really rethink in sustainability terms about the metal manufacturing sector, and steel is only one of the many metal alloys. So a technology that has been investigated and recognized as potential for contributing to the reduction of carbon emission globally is additive manufacturing or 3D printing that starts from a digital model to produce instantly a three-dimensional object by depositing layer above layer, and it can be applied in different materials and sector, as you can see here, from the aerospace sector to the fashion sector. But the focus for today would be on a specific 3D printing technique called work additive manufacturing, which is used for metals. In particular, is using very high heat sources and processed gas, and is using metallic wires, and is depositing them like one above the other one. And I will present you some example in relation to WAAM applied to one of the demonstrators that we have in the European project, that is a boat propeller produced by MNES. And actually also in the literature has been recognized potential of WAAM for boat propeller manufacturing. So now I will move on an explanation of what is a life cycle assessment. And we can start by thinking about a grinding machine. So let's take the life cycle of the grinding machine. For using them, you need energy sources. And then to produce it, it will need to be produced in a factory, which will involve transportation and also raw materials for production of the grinding machine. And once it's used and is not anymore useful, then it's going to waste. And for it, it can be recycled both and reused for making another grinding machine or another products, or it can also be landfill or incinerated. So there are different waste treatment processes that can be considered for the grinding machine. So a life cycle assessment takes into account an approach in which all the life cycle stages of a product, from the resources and material to component and semi-component, the manufacturing, the use of the product, and the disposal of the product are considered. So it's an holistic approach that takes into account all of the life cycle stages. And this would be actually the cradle to grave life cycle assessment. And each of the life cycle stages itself consider different processes called unit processes, and these have as input raw materials and energy, and as output waste, emissions, and products. All the unit processes then can be used to compile an inventory of emissions that then are used in software with standardized methodology to calculate the environmental impact for several environmental impact categories. As you can see here, global warming, acidification, etc. are presented. And in the case here is used for comparative assessment of product A and B. And this is actually the use that we are doing for the Grade2XL. So we compare different manufacturing techniques for the same product. And in addition to that, life cycle assessment also is following precise framework and guidelines and standard, this ISO standard 14040 and 14044. Now that I gave a brief introduction on LCA, I would like to continue with an example. As I mentioned before, it would be the boat propeller produced by MNES. And this is currently produced through casting. And in the project, we are testing it for work additive manufacturing. And so for performing comparative an LCA in general, you need to define a functional unit that is a function of the product, and this allows to compare a fair comparison of product with similar function. All the inputs and outputs of material and energy in the system can be compared in a fair way. And in this case, for the boat propeller, the functional unit is enabling the average propulsion of a fully loaded average fishing vessel for 20 years. And then there are more assumptions underlying behind the functional unit when it's mentioned as average propulsion and average fishing vessel. And then another important aspect to define is the reference flow. But first, let's start by looking at the weight of the casted propeller and the WAAM propeller. We can see that the casted propeller is actually lower in the total weight than the WAAM propeller. Now, before the definition of reference flow, I would like to mention two circular economy strategies that are considered for the boat propeller produced with WAAM. And the first one is to rethink to make the product more use-intensive. Indeed, is estimated that the boat propeller produced with WAAM can have an extended lifetime of about 9 years. And then the reduce as to make increase the efficiency in the product manufacture or the use of it by consuming fewer natural resources. And in this case, it would be the fuel consumption during the use of the boat propeller. And it's estimated that this is about 0.1% thanks to optimized design of the boat propeller. So thanks to this 9-year prolonged lifetime, now we can define the reference flow, that is the amount of products that you need to purchase in order to fulfill the function. That is a functional unit that I presented in the previous slide. And so we estimate that the lifetime of a boat propeller on average is 20 years. And now with the WAAM propeller, it would be 29 years. So the reference flow is actually lower than the total weight of the propeller for WAAM, as the lifetime is a relevant parameter to consider in the assessment. And here I present the system boundaries or the processes that are considered in the life cycle. So it starts with the raw materials needed to manufacture with casting the boat propeller, and then is also considered the manufacture of the finishing and the assembly of the part of the propeller, the use of it during the propulsion of the fishing vessel, and finally the disposal. And similarly is also done for work additive manufacturing, and the material used are slightly different, is steel and Inconel instead of bronze. And as you can see, is also considered other materials as the processes gases that are needed during work additive manufacturing. And so with these processes inserted in a software called CIMA Pro, then we were able to calculate the impact score. And so we use CIMA Pro and EcoInvent as database. And as a methodology to calculate the score, it was used Recipe 2016. And these scores are internally normalized as it gives like a overview of the environmental impact. And as you can see, the use is actually very contributing to the overall life cycle of the boat propeller. And for conventional manufacturing, the use stage is actually much larger environmental impact than for work additive manufacturing. So if we disregard the use stage, we can see that the second one of the processes of the life cycle that contribute the most are actually the material and manufacturing. And for work additive manufacturing, also the energy use during the manufacturing is contributing quite a lot. While the dispose of the boat propeller is actually a negative contribution, as through like when you do recycling, you have a discount of the environmental impact. And now let's shift the topic, and I would like to briefly introduce the life cycle costing that is usually done during a planning phase, and it attempts to estimate the product cost over the lifetime. The boundaries that we are considering is only a financial life cycle costing, which consider all the life cycle stages of a product, similarly to the life cycle assessment. And there are several different categories of costs that can be considered, from design to marketing, the manufacturing cost, fuel or energy consumption cost, for example. So it considers both a customer and a company perspective. Finally, is the life cycle costing is the cost minus the revenue associated with a product. And here I provide an example of life cycle costing cradle to gate. So it's taking into account only the company perspective. And in here, the cost is actually associated to the solid to cavity ratio. And we can see that is lower, is more advantageous to use WAAM for lower solid to cavity ratio than higher, as the intrinsic property of additive manufacturing and the ability of it to produce more complex shapes. Now, I hope there is some time for doing a very fast quiz on Mentimeter. So I would ask you to connect to the voting system of Mentimeter. You can Google Mentimeter voting and insert the voting code that you see here, 15, 78, 64, and 39. So now I will stop sharing the presentation and share the quiz.
Valentina, I didn't have time to see the code. Can you say it again?
Maybe I can post it in the chat.
Yes, please.
Okay. Yeah, it was fast. Okay. Okay, now it should be in the chat, so you can copy paste it. You should see an interface like this one. And then you can insert the code and submit it. I hope you can see the quiz. 3 people joined, 4, 5. Okay. And everyone has the same answer. Okay. Okay, we wait for some more people to join. as we are 20. So I hope that everyone can see. So no one is thinking about any of the other option. And I don't know if anyone would like to say anything in regards of the functional unit in LCA. Okay. Yeah, I think that everyone got it right. Um, okay. Yeah. Then the next question is an open-end question. So why do you think LCA and life cycle costing are important in your perspective? Any reply is correct? And don't be afraid to write anything. And or if you want to unmute and comment on this, please do it. Who wrote, for example, consistency? Can you argument a bit more on your reply? It's interesting.
I guess it was me. Can you hear me?
Yes,
Yeah.
we can hear you.
Yeah, I do believe it's very important in order for several companies to benchmark and to make sure that we are talking about the same thing. When you look at the newspapers, whatever it is, you can see significant deviations according to what they want to communicate on. So LCA for that is pretty important, I guess.
Yeah, I think is correct indeed. It is really important to have standardized application of the methodology, because even if there are standards, sometimes the scope is different or the application is very different, so you cannot really compare across the existing studies sometimes. So it's really important to be consistent and apply the same methodology in order to have more transparent and comparable studies across different studies. So yeah, thanks. Mind change is also interesting. I don't know if who wrote it would like to intervene and say something about it. Or emergency also. That's are interesting. Yeah, I think it's important to have a mind change, like consider to sustainability more in the manufacturing sector. Yeah. I don't know if who wrote it has any, or anyone else has suggestion on how to actually do it even more, the mindset change towards sustainability. Or a lot of replies are actually CO2, carbon dioxide emission reduction, or carbon dioxide emission. LCA is actually also about different environmental impact categories, more wide than simply a carbon footprint. We consider also acidification and eutrophication, so many other environmental impacts. I don't know if anyone else would like to add something on the presentation or in general on sustainability and life cycle assessment and life cycle costing.
Yeah, you can also write down in the chat your questions if you don't want to speak out. But thanks a lot for Valentina.
Yeah.
Also for the interactive session. It's really nice.
Thank you. Yes. Yeah, I don't know if anyone want to, as Lucy mentioned, to write in the chat any questions in regard to the presentation or to the European project. That should be in relation to sustainability and circular economy.
I do have a question.
Yeah. Hi, Daniel.
Thanks for the talk. Yeah, in your opinion, how difficult it is, because of course this, when you use either CIMA Pro or the software for using for doing the LCA, how difficult it is to get the data from the databases and to access, because sometimes, I mean, it's hard to get. Of course, we always trust in databases, right? But we need data from the industries to kind of feed up these databases in order to do the model. So how is the status on the current databases, and how is for you as user to kind of introduce new data, or if a company wants to do their own and they know the data to add on and create a simulation of or comparing different processes.
Yeah, it's a good question. So currently there are many different databases on LCI data, lifecycle inventory data. One of the most diffused is EcoInvent, and is also very well established, and the updates on the data is actually every couple of years. So it's very well updated. And then there are also many other databases. Maybe I can show you shortly. I don't know if you can see actually my internet, or there is even this project called GLAD that shows for any type of product or process different databases that are available in regards to that product or process. Is called GLED, and that is is given, like, for example, EcoInvent maybe might be lacking for more byproducts, like or from agriculture products, and there is Agribalis that is another database. And in regards of collection of data to make average processes that could be representative of a product, then there is an initiative that is called the Unit Process Lifecycle Initiative, in which there is a joint effort of data collection in order to create average unit processes that can be representative for lifecycle inventory data. But for sure is needed the support of industries to collect and provide data. In particular, if it's something very specific, a specific product produced with a certain energy or certain amount of waste or materials, then it would be very relevant to make it case specific with the effort and the willingness of the companies to provide data. And even like a collection of data is an old process. It has different steps, and in the literature is even identified how to do these steps, and is also an iterative process. LCA is an iterative methodology. So once you collect the first data and implement a first model, then you need to refine it in order to get a representative study. Don't know if you have any follow-up, Daniel or Ciprian also can speak about it, or yeah, I don't know if it's the time to move on.
If I can intervene, then if we speak specifically of additive manufacturing, I think we lack quite a lot of the life cycle inventory data that would be needed. I think in terms of conventional manufacturing, it's very well covered within these databases, but additive manufacturing is still a developing area. So there's still room for collection. And I think there's not really much out there, only specific case studies which use their own specific data. Nevertheless, if from the perspective of industry, it is not that difficult to, if you have access to your own data, to construct inventories and then merge with background data and get studies going. So that should not be a problem. It's from a research perspective, we sometimes have difficulties gathering all this data.
Yeah, that's true. It's nice when there is the involvement of industries.
It's also nice to also know that they could also feel free to just create their own database and play with that. And from last question maybe, but from your experience, you think that also industries are more open to kind of share that type of information, no? To put that information into the public databases, or what was your experience on that?
Yeah. So my experience on that so far is that since actually for additive manufacturing is an emerging technology and is still in development, so I think in general a lot of industries are interested in developing like LCA and life cycle costing. And then about public data, I think yeah, there are maybe some confidentiality issues with some of the data. So yeah, in order to, sometimes it's actually difficult to provide like exact numbers and make them freely available for everyone. So in particular because it's like in research and development as a technology. So as Ciprian mentioned before, is actually like the mainly available data are for conventional and well-established processes. But for additive manufacturing, there should be more joint effort of collecting data in order to make average processes for it. So there should be probably a parallel effort on data collection and also making them public, publicly accessible for everyone. And maybe that would be possible in some years, not currently, as there is really a lot of research on it. So probably now is more for internal use and public use, even if usually indication of environmental impact is not a problem. It's more maybe in the use for process gases or electricity input and other. But there is, with LCA, there is also the possibility to actually consider the real value or provide ranges and develop an uncertainty analysis that would make the LCA study quite robust, and it would compensate the difficulty of making the data public from the industry's perspective. Yeah. I don't know if it answered.
Thanks. Yeah. Thank you.
Okay. Yeah. I don't know if there are any other questions as well, or should we continue with Ciprian presentation? What do you think, Lucy?
Yes, if there are no more questions, we can move forward and leave the floor to Ciprian. Thank you, Valentina. Thanks a lot.
Yeah, welcome.
Ciprian, do you have some slides to share? Yeah.
Yes, I'm trying to do that.
Okay, thank you.
I don't know, are they visible?
No, we can see the
You can see
participants.
yourselves.
Yeah.
Sorry about that. I'm having a bit of a difficulty.
I think you can also share the screen and then share the presentation in the screen.
Yes, I think that I can't find the specific application for some reason. Okay, but now?
No, we still can see the participants.
Okay, screen. There we go.
Otherwise, I can share the presentation as well.
Now it should work.
Okay,
Yes.
yeah, perfect.
All right.
Yeah.
Sorry for the delay. So I'll try to fit into the remaining time. As said at the beginning, my name is Ciprian Cimpan. I'm an associate professor at the University of Southern Denmark, the section of life cycle engineering specifically. And I'll give a short talk on circularity and resource efficiency in additive manufacturing. I first want to start by saying that in 2020, when the European Commission was doing a large number of studies in order to update the list of critical raw materials for Europe, they specifically listed 3D printing or additive manufacturing as one of the technologies that are crucial for a number of sectors and also for having a climate neutral economy in Europe in the future, which is quite positive, I would say. Additive manufacturing today is a very small part of manufacturing overall. However, it's predicted that it will increase if almost exponentially in the future. So lots of promise there. The technologies are also considered a major enabler of certain circular economy strategies, such as repair and remanufacture, shortening of supply chains and reshoring of manufacturing and recycling, and also enabling more local circular manufacturing ecosystems. Despite the fact that additive manufacturing has moved from pilot scale to more industrial scale, we still don't have a lot of sustainability assessments on the different technologies, or they are quite simple at the moment. In any case, taking a look at the available literature, we find quite some examples. And here are some graphs of results on the left side. The taller graphs that you see are generally related to conventional manufacturing, meaning that they show higher impacts compared to the smaller bars, which are additive manufacturing. And in the middle graph, you can also see that the blue part is actually related to materials production, which is also quite an important aspect that I'll emphasize during this presentation. So we have these examples, and we have even people that have tried to put together a lot of different lists of what are the value generating aspects and environmental aspects related to that for the technologies. So, for example, shape complexity and reducing subcomponents, topology optimization and improving function are certainly very big value generating aspects. And in terms of environmental influence, they potentially can increase the life of products produced in this way. At the same time, they can potentially create difficulty for materials in these products to be recycled at end of life. We have also lightweight design, of course, reducing transport, packaging, near net shape, high feedstock utilizations, which reduce material use and waste during manufacturing. And of course, when we talk about more local ecosystems, additive manufacturing can reduce product lead times and stocks and so on, again, reducing transportation infrastructure and potentially even resources. However, there are still a number of critical areas that need attention. There's a lot of potential, but there's also some areas that need more assessment. One of the aspects that I see looking at LCAs of additive manufacturing is that many times the results are dependent on how we define this function or the service or the product that is assessed in the study. There's typically nonlinear dependencies between, for example, part size or number of parts. And another aspect that's really comes through in many cases is solid to cavity ratios. So in terms of how you define this aspects, a product can very easily become better produced with conventional manufacturing than with additive manufacturing. Then there's the aspect of process efficiency, which is quite crucial, but far from optimal today. We have to still look at feedstock utilization rates and especially energy consumption and also other consumption of consumables, other consumables used in the process. Post-processing is sometimes missing in LCAs. And last but not least, maybe from my perspective, one of the most important aspects is that resource circularity is rarely touched on in LCAs. So aspects such as design for recycling and how alloys and products are designed has to be more more assessed. One of the aspects related to specifically how the boundaries of studies are defined, many studies are only cradle to gate, meaning that they don't include the use and the end of life of these products, which is a problem. And I'll now take each one of these a little bit individually, and I'll start with energy efficiency of additive manufacturing processes. You have a table here which shows in the second column the theoretical specific energy consumption, and then the next column is the real energy consumption, and the last column shows an efficiency rate. And most processes that deal with additive manufacturing show very low energy efficiency. And this is, of course, an important aspect. For instance, if we talk about feedstock production, powder specifically, you can see in this graph, a kilogram will require 25 to 30 megajoules of energy to produce. HIP is different because the powder can be much more coarse, so therefore the energy is much less. But comparing this to the preparation of the material for conventional manufacturing, let's say melting, pressing and cutting of steel, for instance, that will never be more than 3 megajoules per kilogram. So we are talking about much smaller figures. If we go then into some of the manufacturing processes themselves, the ones that use lasers, for instance, are quite inefficient. On this graph, you can see most of the energy as electricity at the beginning, only a minor fraction of that actually becomes used energy in the melting spot. Nevertheless, there are ways to optimize energy efficiency, and additive manufacturing is still under development, so therefore this will change in the future, I'm sure. So for instance, better utilization of volumes and the increasing number of parts or increasing the time of manufacture will obviously decrease the energy quite a lot. I'll go then next into aspects of resource utilization or feedstock utilization rates. It can be shown in different ways through solid to cavity ratios and complementary also by to fly ratios. And I give a couple of examples here. In this graph, you can see the bars represent masses of flows of materials. On the left side is the additive manufacturing process. On the right side bar is the conventional manufacturing. And then the blue part is the actual material that stays in the part. And the rest are waste basically removed in the process. So as the solid to cavity ratio increases, you can see there's less difference between conventional manufacturing and additive manufacturing. So that less waste, and this has, of course, an impact on environmental aspects, energy, as well as cost and time, of course. So what this graph down here shows, for instance, for energy and CO2, which are the first two, is that a break even occurs somewhere at a solid to cavity ratio of 0.6, between 0.6 and 0.7, where any benefits from additive manufacturing become then negated. So the additive manufacturing, being the red circle line, is doing much better until this break-even point. And that is determined in this case by an increasing solid to cavity ratio. So this is quite important. Complementary to this, it can be seen from a different perspective, again comparing wire arc with conventional casting and milling processes. In the same way, then the benefits of additive manufacture are completely connected to the buy to fly ratios. So as soon as we have very low buy to fly ratios also for conventional manufacturing, then the benefits of additive manufacturing are not there anymore. So there's a threshold always. But these are the processes themselves. If we take a look more widely at the whole supply chain, so let's take, we have the production of the material, the preparation of the feedstock, and the manufacturing as the last one. And we compare the two. Theoretically, there's been, this study has done quite a nice comparison between additive manufacturing at a buy to fly ratio of 2.2 to 1, and then compared to subtractive manufacturing at different buy to fly ratios, and then including all of the transportation that would be needed to deliver a part of 10 kilograms to a user somewhere in the world. And what was then important? What did they find? They tested a large number of parameters, and what you see basically here: package size, weight, the different types of transport, distance, and the buy to fly, and the energy mix for manufacturing as well. The weight, of course, if you have a larger part, then of course it's all linear to that, the impacts. However, what's important here is that the types of transport and the distance didn't really make any difference, while the buy to fly ratio made a huge difference, and also the energy mix in manufacturing. So these are two aspects which really, really are important, and less so the transportation involved and the supply chains in that. Now, I will move back to design for recycling. This is the third aspect. Just note down your questions if you have some for the previous slides. So first I'll say what critical raw materials are. So critical raw materials are resources which are either scarce in geological terms, they have complicated supply chains, and they may face supply risks. And lastly, and most importantly, they are extremely important economically or strategically for different sectors of an economy. In this case, with the example of the European Union here, so additive manufacture itself, highlighted second to last, it uses some resources which have a high supply risk. It also supplies products to important sectors such as renewables, e-mobility, and defense and space. On the right side, you see the result of this assessments at EU level. So 30 raw materials were defined as critical raw materials. Now, a little bit more about what is scarce and why a material would be critical. the table of elements on the left side shows for each element 3 different measurements. So on the low triangle, you see abundance or scarcity. That's geological scarcity. And on the upper part, it's a measure of how concentrated production is and how concentrated the reserves are. That means how many places in the world have the resource and how many places in the world actually produce the material. And you can see that some of the materials are actually quite scarce, but also maybe have very concentrated reserves and even concentrated supplies or production. If you take the last row of elements, that's mostly the rare earth elements, you can see that production is highly concentrated. You see some examples also on the right side. So rare earths, the production and the resources, where the resources are extracted, are mostly in China. So that means that we have a supply risk. And when these materials on top of it are very important for an economy, that makes them critical. That's half of the equation. The other half of the equation is how well are we able to recover these materials at the end of life? And in this graph, you see percentages of input of secondary materials to production in Europe. As you can see, only very few, the blue ones, have high recovery and then use in new products. And a lot of them have very small recovery rates at the end of life. So that's obviously a problem. Moving back to the study that the Commission did, specifically for additive manufacturing. If we take a look at only what was important to this technology, we have some problems in terms of raw materials, because of course raw materials are extracted mostly outside Europe. And we are doing much better in terms of process materials. So the alloys that are used in additive manufacturing are at least more than 50% produced in Europe, and that's quite good. And then assemblies and products are sold all over the world, but also a lot of them still remain in Europe. What this means is that although we don't have much control over raw materials, we have a lot of control over alloys, process materials, and over the products at the end of life. So recommendations are that we have to be better at recycling and reusing these in order to reduce constraints on supply of raw materials. Another thing would be to diversify the material supply as much as possible or substitute for other materials. Yes, and for additive manufacturing, what we can think of when we talk about design for recycling is 2 main areas. So materials, alloys specifically, should consider the limits of present metallurgy. So how well can you separate the different elements from each other afterwards? The second aspect is on the product level, so product design. This should be also taken into consideration. So aspects such as liberation, how different parts are then separated and sorted, is really important for how well you can recover different elements then in the final metallurgical processes. And below you see an example of a complex product such as a vehicle. What happens, you typically shred, and then you will sort into different concentrates, and these concentrates will always be different mixtures of different materials. They go to different metallurgical processes which have limitations, and then some materials can be recovered and some cannot. What you can use in order to estimate what will happen is, for example, this compatibility matrix. Which takes into consideration what happens in the metallurgical processes. So essentially, there are different elements that can be combined together in alloys, and then they will be easy to separate from each other later on, and that's the intersection that is green in this matrix. Yellow, it means that some of the elements will just stay embedded into the alloys but not have any functional use. And the red is where actually combining these two elements will create a problem. So one of the elements may become maybe a tramp element, destroying the properties of that alloy. Very well-known example of that is having copper and steel together. But there are many others here, like having chromium together with aluminium, with copper and zinc and lead, for instance. So there are some combinations that are then much harder to treat at the end of life due to basically limitations of the metallurgical processes today. A nice way to capture this is given by the metal wheel of Markus Reuter. So this metal wheel, which you see on the right side as like a pizza cut in slices, shows the interaction between having complex mixtures and materials and how they would react being taken to a specific metallurgical process. Again, green means recovered, red means lost. And each slice basically refers to one type of metallurgy. If you take the 11 o'clock to 12 o'clock slice, which is iron metallurgy, you can see that most of the materials become embedded into the alloys, such as nickel, cobalt, chromium, and so on. Some of them will get lost. Gold, for instance, which is a precious metal, will be lost, and so on. The different levels of the slice denote where the materials end up. First, it would be in alloys, and the other slices represent basically residue streams. And you can see that different technologies or different metallurgical processes have different requirements, basically, in terms of what they can separate from each other. And that's really important. I hope this was not overly fast, and I have some final thoughs then. So additive manufacturing is still under development, and of course it will optimize in the future. We need to optimize especially the use of energy in consumables. We have a need for more models that find break-even points and help make process choices based on multiple criteria, basically. So which process do you actually choose for making a specific part in terms of efficiency, but also sustainability aspects. We need more sustainability studies that consider cradle-to-gate boundaries, and we lack data in many cases to that. Material production and feedstock preparation is often the largest impact contributor in additive manufacturing. So that's why we do need to focus more on the materials. We need more consideration for design for recycling within the industry. And here, the importance of element compatibility for circularity is really, really crucial. And with that, I will stop and welcome any questions.
Thanks a lot, Ciprian. So if you have any questions, feel free to speak or to write down in the chat. I actually have a question, but maybe for Valentina, because it's more specific to Grade2XL, but this challenge of the recycling of the parts that are built with WAAM, is it taken into consideration in the project?
Yeah, is like there are some consideration on it. Not in the perspectives that Ciprian presented today with this nice report from the European Commission. The metal recycling wheel is actually very nice, and it's interesting to see that we lose so much of critical materials through the supply chain and the recycling. And yeah, I think that is something difficult that we don't consider that much at this stage in the project, I think. But it would be nice to consider it more. So as Ciprian was showing, there are different type of design that we that he presented, right? So the design for the functionality of the product, it is also very important, the design for recyclability. And yeah, it would be nice to integrate it more. So it's a very good suggestion and nice that he contributed with his reflections on the topic. Yeah.
And often it is the minor elements that are in these alloys which are most precious, and they carry very large environmental impacts in their production. So of course, a high alloyed steel could be recycled only for the value of the steel, and with losing the functionality of the minor elements. But then you actually only maybe use 20% of or you recover 20% of the environmental impact that was spent at the beginning in order to make that initial alloy. And we don't have very good metallurgical processes to recover a lot of the minor alloying elements within different categories of alloys.
Yeah, we also talk a bit on multi-material additive manufacturing. That is also part of the project for functional grading. And that could face more difficulties in the end of life in the disposable part of the product. So that would be something interesting actually to investigate more, for sure. Closing kind of the loop of material use and recycling is not easy. Yeah.
No,
I think
it's something that has to be at least put on the agenda first. And there are, for example, the compatibility matrices could be quite useful in order when you look at designing new alloys, for instance.
Mm-hmm.
I have a question for Ciprian.
Yes, Thomas.
Yeah, hi. Thank you for the very nice presentation. I think it was a lot of information, and also learned something. It was really nice. Also, especially the metal wheel. I like that a lot. And because I think right now in additive manufacturing, what we see a lot is that everyone thinks of making new alloys, and there's so many companies that want to profile themselves with offering new alloys and mixing different materials together. We also have high entropy alloys where they even mix more of those precious or rare earth elements together. And maybe there should be much more focus on actually reducing the amounts of different elements, because especially in additive manufacturing, there are some possibilities to design hierarchical microstructures to actually get strength without alloying extra elements. So I think it's really important to design for recyclability from the beginning and have less alloys in the end, so they're easier to recycle.
I think the aspect of standardization is still something that's very much in the works, right, in relation to additive manufacturing. And of course, this also goes into the alloys themselves. I think it's when you have new alloys which to gain specific functions, then that should be measured. Is the additional function worth it environmentally wise to losing maybe some of the resources that you put in the products themselves? So that could be something that could be compared. And of course, resources are limited. We don't have more. So that's an important aspect. And of course, what you mentioned, Thomas, about using the basically the shape itself, or how the product is made in order to gain that functionality. I think that's a very interesting aspect.
Yeah. Thank you.
Thank you as well, Thomas.
Any more questions? So if not, I will just thank very much our speakers today. Thanks a lot, Valentina and Ciprian, for the very comprehensive presentations. For the participants, thanks for being with us today. If you want to be kept informed about the Grade2XL project developments, you can follow us on LinkedIn and register to our newsletter. If you have any questions, of course, I am available and you can reach me via email. And don't forget, our next webinar will be on 25th of November, same time, 1 p.m. And it will focus on the applications of WAAM to the maritime and offshore sectors. And we will talk about the propeller that Valentina mentioned in her presentation. So thanks a lot. We hope you enjoyed the webinar, and we see you soon.
Bye-bye.